Let's take advantage of algebra to show that the inverse hyperbolic sine is indeed this natural log function on this particular domain. We'll start with letting y equal the inverse hyperbolic sine of x. If and only if the hyperbolic sine of y is indeed x. Now we're going to substitute using the definition. And at this point, the equation is set equal to 0, and we're going to multiply both sides by e to the y. In doing so, we get this equation. Now this equation is quadratic in form. If you notice that m is equal to e to the y, then this equation is quadratic in form, and we could go ahead and use the quadratic formula to solve for e to the y. E to the y is equal to the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. What we're going to do now is factor and so we're left with two cases. Either e to the y is equal to this positive valued function, or e to the y is equal to x subtract this radical here. But since e to the y is greater than 0, we only have this equation. In other words, this is extraneous. Notice this is false. Just test x equals 6. Now going back to this equation here, we're going to take the natural log of both sides. And using log properties, we know y is equal to the natural log of x plus the square root of x squared plus 1. But what is y? Remember, y was substituted early on. Y was substituted as the inverse hyperbolic sine of x. And notice the argument of the natural log function is greater than 0 for all these x values in this interval. I'll leave it as an exercise for you to find the inverse hyperbolic cosine of x as a natural log function. Let's take a closer look at the inverse hyperbolic tangent function. Remember, the inverse hyperbolic tangent functions have nothing to do with angles, so we're strictly going to rely on our language of algebra to figure out that this is a natural log function. Let's begin. We'll let the inverse hyperbolic tangent of x equal y if and only if the hyperbolic tangent of y is indeed x. Now we'll go ahead and substitute. And we're going to multiply this by a special 1. And off to the side, we're going to go ahead and use long division. Now we get this nifty equation, and our goal is actually to solve for y. We need to find a common denominator. And we finally get e to the 2y is equal to 1 plus x over 1 minus x. Clearly, x cannot be 1. We're going to go ahead and take the natural log of both sides. We're going to use the inverse function here, which is the natural log function. And notice we finally got y by itself. But remember what y is. Y is the inverse hyperbolic tangent of x. And now that is equal to 1/2 the natural log of the argument 1 plus x over 1 minus x. Now you got to remember, we need 1 plus x over 1 minus x to be greater than 0 in order to satisfy the domain of a natural log function. Well, how do we do that? We need to test the intercepts. I should say we need to test around the intercepts of the polynomial in the numerator, and we need to test around the intercepts of the polynomial in the denominator. So we'll put those intercepts on a number line. The x number line, and we're going to test around these numbers. And what are we testing? We're testing this function here. So if you test r of -2, notice we get a negative value. So that is false. We don't want false. Let's test r of 0. Notice we get 1, which is true, meaning is it 1 is greater than 0, which is what we're trying to test. We want to know when the x values are greater than 0. So this is true. I'm going to shade that. And let's test r of 5. If you test r of 5, we get a negative value. Once again, that is false. So we're just using algebra and realize that, oh, the domain must be what? The domain must be between -1 and 1, and that is the end of all the algebra here. Let's go ahead and use implicit differentiation to show that the inverse hyperbolic tangent, inverse hyperbolic sine of x is indeed equal to this function of x. We'll begin by letting y equal the inverse hyperbolic sine of x if and only if the hyperbolic sine of y is equal to x. We're going to take this equation and implicit differentiate with respect to x. You got to remember, y is a function of x here. So if y is a function of x, then we have a chain rule with the derivative on the left-hand side. We're going to take the derivative of the outside function, evaluated at the inside function, which is that, times the derivative of the inside function, which is simply dy dx. On the right-hand side of the equation is simply 1. And now we have dy dx is equal to 1 over the hyperbolic cosine of y. But what is the hyperbolic cosine of y? With the help of a hyperbolic identity, we can manipulate this following expression. Finally, we are ready to substitute. What was y? You're probably wondering, where did this square root come from? But we already know that the hyperbolic cosine function is positive. And so there you go. That is the implicit differentiation. Notice it's mostly algebra. Algebra is such a powerful tool. Let's use implicit differentiation to find a derivative of the inverse hyperbolic tangent of x. We'll begin with letting y equal the inverse hyperbolic tangent of x if and only if the hyperbolic tangent of y is equal to x. From here, we're going to implicit differentiate with respect to x. You got to remember y is a function of x. So in this particular case, we're going to see a composition of functions and we're going to need a chain rule. We need the derivative of the outside function evaluated at the inside function. Well, that's simply the square of the hyperbolic secant of y times the derivative of the inside function, which is simply dy dx. The right-hand side of the equation is simply 1. Now you're probably wondering, what is this expression here? Well, we're given a trig identity. I'm sorry, that is not a trig identity. We're given a hyperbolic identity. So why don't we manipulate that? We're ready to substitute everything in. What's y? Y was the inverse hyperbolic tangent of x. And on the right-hand side, that's simply 1 over 1 minus x squared. We got everything. The beauty of algebra.